Welcome to today's video. This video comes under the Biostatistics playlist of the channel. The videos under the Biostatistics playlist begin with the alphabet A. They have been numbered to facilitate easy learning. The order in which they have been uploaded may be different, but when we follow the numbers, it is easy to learn. Earlier, we have seen how ANOVA test can be done using the Excel data analysis tool pack. Today, we'll be seeing how to do the manual calculation. As we all know, ANOVA stands for Analysis of Variance, and this test can be used to compare the significance of difference amongst more than two sample means. Normally, when we have to compare two groups, we use the t-test to compare. When we have more than two groups to compare the means, we can use ANOVA. The assumptions for ANOVA are the data within each group should be approximately normally distributed. Similarly, the variance of data within each group should be approximately equal, and the observations should be independent of one another, and the sample should have been selected by random sampling. The test characteristic that we calculate in ANOVA is F value, which is given by the variance between samples by variance within sample. We have already seen that whenever we use a software package to do the calculations for any type of test, we will directly get the p-value, and whenever p-value is less than 0.05, it indicates statistical significance. Whereas if we are manually calculating, we have to then see if our calculated value is greater than the table value at 0.05 level of significance. If the calculated value is greater than the table value, null hypothesis can be rejected, and we can say that there is a statistically significant difference between the groups. This we have seen in our earlier videos also. So suppose we have a problem like this. We have 15 sample plots under 3 different treatments. So we have 5 plots for each treatment. Now we are comparing, for example, let the treatment be seed variety. Then we are comparing the yield for the 3 different seed varieties. Since we are comparing one criteria, this is one-way ANOVA. If we are also comparing another criteria simultaneously like soil quality, then it becomes two-way ANOVA. This is an example for one-way ANOVA. This particular example, I have taken 3 groups because we are going to do the calculations manually, and to understand it will be easy. So we have chosen this example. So the first thing that we have to do is, let us consider the treatments A, B and C as X1, X2 and X3. This is just for convenience because whatever formulae we are going to employ in the following steps will be using this terminology. So the first thing that we have to do is we have to add all the items under X1, so you get sigma X1. Add all the items under X2, you get sigma X2, and add all the items under X3, sigma X3. So this is the preliminary things that we have to get ready. This is a shortcut method for one-way ANOVA. Next one is we have to find out sigma x1 square. That means we have to square each item under x1 and then you have to find out the sum. So 20 square is 400, 21 square 441, 23 square is 529, 16 square is 256 and 20 square is 400. If you add all this, you get sigma x1 square, which is 2026. Similarly, we have to do for x2, you have to square all the terms and then find out the sum. And similarly, we have to do for x3, we have to square all the terms and then find out the total. So we have got all these terms. This we will be employing in the upcoming steps. So the first step is finding out what is the correction factor. So whatever we have calculated in the previous slide, I have put it here so that it is easy for us to use it for calculation. The first thing is correction factor, which is t square by n, where t is the total sum of all the items. So you want the sum of all the items. We can get that if we add sigma x1, sigma x2 and sigma x3. So it is 100 plus 95 plus 135, which is 330. Correction factor is t square by n, 330 square by 15, which is 7260. The next step is we have to find out the total sum of squares, which is sigma x1 square plus sigma x2 square plus sigma x3 square minus t square by n. T square by n we have already calculated 7260. The first step that we did. Now, we need sigma x1 square in this case. So, it is 2026, 1863 and 3701, which we got by squaring each of the items under the different treatments and adding it. So, you have to add all this and then subtract 7260 from that, and we get it as 330. The next step is sum of squares between the samples. For this, the formula is sigma x1 the whole square by n plus sigma x2 the whole square by n plus sigma x3 the whole square by n minus the correction factor. We have to understand that this is different from sigma x1 square, which we used earlier. There we squared all the items and we took the sum. Whereas what we need here is the square of sigma x1. So here we have to use 100, 95 and 135, and that term has to be squared. So there is a difference. Sigma x1 the whole square is different from this sigma x1 square. So 100 square, and in each group we had 5. So 100 square by 5 plus 95 square by 5 plus 135 the whole square by 5. So these are the terms which we get: 2000, 1805 and 3645 when we solve each of these terms. So we have to add all this and subtract 7260 from this. So we get the value as 190. So in the previous two slides, first thing we found out was total sum of squares, and the next thing which we found out was sum of squares between samples. These two values are required, so I have put it here. Now we have to find out sum of squares within sample, which is total sum of squares minus sum of squares between the sample, which is 330 minus 190, which gives us 140. The next step is we have to prepare the ANOVA table. So this ANOVA table, we get it when we do the test using a software package also. We have already seen this when we used a data analysis tool pack. We will get this ANOVA table, we'll get the F value and we also get the P value. So here we write the source of variation. So between samples and within samples. So between samples, the sum of squares we got is 190. Within sample we got 140. Total was 330. So 330 minus 190, 140. Now what are the degrees of freedom in each case? Always degree of freedom is n minus 1. So we had 3 treatments. We had 3 groups. So 3 minus 1, 2. Similarly, within sample, so we had 5 in each group. So n minus 1 means 4. So 4 in each group, 4 into 3, 12. So here we put the degree of freedom is 12. The mean square, you have to divide this by this. So 190 by 2 is 95 and 140 by 12 is 11.6. If we have these two terms, we can calculate the F value. So the F value is variance between sample by variance within sample, which is 95 divided by 11.6, which is 8.26. As we saw earlier, now we have to see whether this calculated value is greater than the table value. Only then we can draw the inference. So at 0.05 level of significance, we can check. So this is for 95% level of confidence. So first we will check at this level, and then if you need, you can go further. If we see a statistically significant difference, we can check at 0.01 and 0.001. We have discussed all this in the tests of significance video. So we have to check for degree of freedom 2 and V2 degree of freedom 12. That means in row 12, you have to check under column 2 in the F table at 0.05 level of significance. The value is 3.98. So the calculated value is greater than the table value. Therefore, the null hypothesis is rejected and we conclude that there is a significant difference between the groups. When we do an ANOVA test, if we do not find a significant difference among the groups, so we can stop with that. Whereas if we find a significant difference, the next step will be to find out between which of the groups there is a difference, because when you have five groups, there may be difference between two groups and we may not have a difference between another two groups. So we have to find out between which of the groups we have a difference. For that we will do tests which are called as post hoc analysis. So we have a variety of tests like Dunnett test, DMRT, two keys test, etc. And we have software packages which you can use to do that. So that will become necessary whenever we find that there is a statistically significant difference. Thank you.